Okay, well, first of all, I would like to thank you, Orkun, for inviting me to give this lecture, and also to Dr. Sabi Anwar, if he's listening to this talk. It is certainly a great pleasure, but I think my pleasure would have been enhanced tremendously if I were physically there in Istanbul. I mean, my wife and I have traveled to Turkey many times and have every time enjoyed our stay in Istanbul and some other cities of Turkey. So it's certainly a delight to be part of this meeting. And also, I noticed that there are some wonderful friends in the audience, both remotely and in person. Dr. Taskin, for example, is, I believe, listening, and he is such a wonderful friend. And I enjoyed listening to this talk by Dr. Manzoor Ikram and Dr. Imran. So it's really a great pleasure. Okay, so what I would like to talk about today is, so the title of my talk is something very similar to the theme of the lectures today and perhaps tomorrow. This is about protecting quantum coherence and entanglement in optical systems, and I present a sort of a version of it using erasing the memory. And the reason why this problem interesting, because it comes from quantum computing, where decoherence is a very big problem, and one would like to get around it. So here is just a very brief introduction about quantum computation, which we all know, and that is that the basic difference between quantum computing and classical computing is that both of them are done through bits, but classical bits are quantities like voltage and current, etc. Quantum bits are essentially quantum states, and they are manifested in many different formats in the laboratory. For example, they could be in the form of a number state, polarization state of photons, spins, spin up and spin down, and energy levels, etc. The sense in which quantum computing has an advantage over classical computer is that quantum bits, they satisfy some properties which are not shared with classical systems. For example, qubits can be formed in terms of a superposition of states. So here I've given superposition of state between 0 and 1. And of course, they can form quantum entanglement.
Just a moment, please. We have a connection. We have a connection problem. We have missed one for last minute. You can repeat one more last minute. We couldn't hear them.
Oh,
sorry.
So you cannot listen to me?
Yeah. We have a connection problem. We had a connection problem, internet problem. We couldn't hear for last minute.
I see. Can you hear me now?
Yeah. We can hear you clearly. All right.
Okay. Well, I mean, this is just a repetition of what you already, I mean, students already know about. So, I mean, here I'm just emphasizing why quantum computing, and the reason why quantum computers are expected to perform much better than classical computer is because of certain properties. And one of them is that the qubits can form coherent superpositions. They can be simultaneously in states 0 and 1, something which is not possible for classical bits. And similarly, quantum bits can form quantum entanglement, states of two particles or multi-particles such that they affect each other. They cannot be treated independently of each other, like we can treat classical systems. So the advantage of quantum computer is essentially comes from quantum entanglement, where we can store a very large amount of information in very small number of qubits. And just to exhibit that feature, let me just mention that if you have only two particles, we can we can store four pieces of information. Here they are listed as C0, C1, C2, and C3. These are complex numbers. If I have four particles, then 16 bits of information could be stored. Then if there are this very small number, 1,000 particles, 1,000 qubits, they can store information of 2 raised power 1,000 bits, which may not impress us until we realize that it is almost the total number of atoms in the entire universe. So this raises this possibility that with just 1,000 qubits, 1,000 atoms, we can do the same kind of calculation as we can do on a conventional computer, where the bits that are involved are all the atoms in the entire universe. Now, this is quite a remarkable realization. But it turns out that nature doesn't give us everything for free. There are two major problems with quantum entanglement or quantum coherence. One of them is, of course, comes from the probabilistic nature of quantum mechanics. That is, that if we have a coherent superposition state, which is fine, but if we try to make a measurement, then the result is probabilistic. So in this case, for example, probability of finding zero is C0 modulus a square, and so on. So this is one problem, and therefore, one has to find algorithms which can be solved on quantum computer much faster, but trying to sort of overcome this problem. I mean, this problem cannot be overcome, but one can get around it. Okay, the other problem that any quantum computing device will suffer from is decoherence, and that is essentially arises due to interaction with surroundings, and they tend to destroy coherent superposition and entanglement. I mean, coherent superposition and entanglement are very, very fragile objects because as soon as they start interacting with the environment, decoherence takes place, which can lead to a lot of errors. And in this meeting, and you have heard probably many lectures, including the previous one by Dr. Manzoor, that decoherence is a big problem. Decoherence is irreversible, and in any quantum computing algorithm, its implementation, what is really needed is try to sort of overcome decoherence. And this is certainly a problem as old as quantum computing. I mean, as soon as quantum computing basic ideas came around, people realized that decoherence will be a major problem, and they tried to find ways to get around. So you heard some talks today, and I'm sure you'll hear something, for example, tomorrow morning as well. Question is, can we reverse decoherence? Okay, so can we overcome decoherence? I mean, the way I pose this problem, and it will become very clear very soon, can we erase memory? Okay. Once we acquire some information, can we just wipe out our memory and start all over again? So that is the way I would look at it. Okay, so there have been a lot of schemes to overcome decoherence. I mean, there have been error correcting codes. There is interaction-free basis, and so on. And the list really goes on. What I would like to talk about today is reversing what we call weak measurement and reversing the amplitude damping. So I'll explain these ideas as I go along. Okay, so the first, I mean, this is the organization of the talk. I don't know how far I'll be able to go through in this limited time. But I would like to first of all explain what is weak measurement. I would like to talk about some ways, generic ways of reversing the weak measurements, and I'll talk about some schemes that we proposed on cavity QED type systems using multi-atom scheme and Zeeman scheme. I'll just give you a flavor of it instead of going too much in details. And then I'll also talk about entanglement reversal as well. And I'll present another approach to the problem instead of weak measurement using some simple logic gates. Okay, and entanglement reversal. Okay. Okay, so let me address the question about this measurement problem. I mean, as we all know, measurement problem is perhaps the most fundamental problems of quantum mechanics, and it is still in a state where people feel very unsatisfactory about. Okay, I mean, because basically quantum mechanics gives us the wave function as I'm showing here, when we do the measurement, then we find one of the states in here, and the question is, how do we get that particular state? And quantum mechanics does not answer to that question. And this is, in my mind, one of the most important problems of quantum mechanics. And it has been a very important problem for almost 100 years now. Okay, but let me just mention how we perceive things here. So supposing I have a quantum state, which is a superposition of 0, 1, 2, and m, and this could be, for example, in a cavity type situation, could correspond to the number of photons. Okay, now the thing is that as long as we don't do the measurement, this is the quantum state of, this can be the quantum state of the system. For example, quantum state of the field inside a cavity. But when I try to make a measurement, then I'll get one of these results. I could get no photon, or I could get one photon, or two photon, or m naught photons. And as soon as I get that measurement, the state collapses to that particular state. For example, if I get an outcome of my measurement to be m naught, then the state collapses to m naught. Okay, and this is a very probabilistic kind of process. But the thing is that once measurement has been made, this kind of measurement has been made, then it is impossible to recover back the original state. We lose all informations about C0, C1, C2, etc. Okay, so we cannot recover the original state after the measurement. And these are the kind of measurements we usually talk about, and they are referred to as strong measurement. I mean, these are what are also called von Neumann measurements, etc. Okay, but what I would like to talk about today is, while talking about erasing memory in quantum systems, reversible systems. Okay, so a reversible measurement would correspond to a quantum measurement if the pre-measurement state, the original state, is uniquely determined from the post-measurement state and the outcome of the measurement. Okay, and in this case, it would turn out that measurement is logically reversible. And in this case, actually, systems information is preserved during the measurement process. Okay, and this is what is referred to as weak measurement. Okay, so in this case, we might like to say that wave function does not collapse to a fixed state, but it collapses partially. What does it all mean? Okay, so let me actually, before I talk mathematically, let me put the problem in this way. Supposing I have a cavity, and the cavity has a quantum state which is a superposition of two states. Either there is no photon or there is one photon with corresponding amplitudes C0 and C1. Okay? So as long as these mirrors are completely reflecting, the state would remain the same. But supposing now one of the mirrors become partially transparent, so a photon can leak through it, and there is a detector outside, and we assume, for the sake of argument, that this detector is 100% efficient. Okay. Supposing the question we ask ourselves is, supposing this detector does not click, there is no photon detected by the detector. Question is, what is the state of the field of the qubit inside the cavity? Is it the same, C0 0 plus C1 1, or is it something else? Okay, so this is a question that we address, and this we address in the context of this weak measurement or decoherence problem. I mean, we can almost never have perfectly reflecting mirrors, especially when we want to get some information about the system. We have these partially transmitting systems, and the question is that if there is no click taking place, can we assume that our system is intact, okay, and in the same state as was there initially? Okay, well, it turns out that that is not true, okay, because what happens is that if we again consider this quantum superposition of states, and here I generalize it to 0, 1, 2, and m photons, and if, so this is the state inside the cavity with partially transmitting mirror, and there's a detector outside and the detector does not click, okay, then that is a kind of measurement in the sense that we get some information about the system, okay. We get some information about the system if the click does not take place. The situation is something very similar to if there are, let's say, some people inside a room. There could be no person in the room, or one person in the room, or two persons in the room, and so on and so on. And as long as the door is closed, we know there are certain number of people in the room. But if the door closes, a door opens, and we stand on the side to watch what is happening. If after 1 minute the nobody comes out of the room, then we can conclude that really there aren't perhaps too many people, and nobody has come out. If we wait for 1 hour, our confidence level that there are very few or no person in the room, that probability increases in our mind. If we wait for almost a day and nobody has come out, then we are almost certain that there is no person in the room. But we can never be absolutely certain that there is no person in the room. Okay. Now the question that we ask ourselves is that this information that we obtained by waiting for 1 hour or several hours or 1 day, can we erase this information and recover the original probability that we had in our mind? Can we erase all that information that we acquired by waiting to see and nobody came out? Can we restore that information? Okay, so the question, okay, now we ask ourselves in this spirit is that if we are given this particular state inside the cavity, what is the state if the detector does not click? Okay, so if the detector clicks, then we know what is inside, and then the game is over. But I'm talking about only those measurements where the detector does not click. Okay, well, if there is no photon detected after a time t, it would turn out that the state that will be there will be now still a superposition of 0, 1, 2, and so on, But you see these factors, e raised to minus gamma t with single photon state, e raised to minus 2 gamma 2 t with 2 photon states, and so on. Okay, these are like the decay rates. These are the cavity decay rates. Okay, so now here, if we look upon this scenario of this possibility of of zero photon or one photon or two photon or m photons, then the scenario is like this, that if there is no, if the detector does not click, that means that the number of photons are less than what we assume. So the largest decay in our information will be for the larger number of photons. Okay? So for example, the probability that there are two photons, that probability now goes down by e raised to minus 2 gamma t, square of that, e raised to minus 4 gamma t. And similarly, for one photon, it goes down like e raised to minus 2 gamma t. Okay, the amplitude is e raised to minus gamma t, and probability is square of that. Okay, and if we wait very long, then of course the probability that is increasing of having no photon inside the cavity. So please notice that in this case, by no click on the detector, we are getting some information about the system, but the system is still intact. Even if we wait for an infinite amount of time, of course, these factors, the probability of a single photon and two photon and so on will go down to almost zero, but never exactly equal to zero. So in this kind of a measurement, we are getting some information, but the nice thing is that in this case, the state is still intact in the sense that the state inside the cavity still has some information about C0, C1, C2, and so on, I mean, which determine what the state is. And the question that we pose ourselves is, can we erase this information and restore the original state? Okay. Now, typically, in the literature, if you go in the to the quantum computing literature, which is very, very extensive, very old now, I mean, the concept is that this decoherence is irreversible. If we acquire some memory, then we cannot wipe out that memory completely. Okay, I mean, we all know that if we are become aware of something, we cannot just wipe out that memory and start all over again. Same thing here. So the question is, can we wipe out this information and restore the original state? Okay, so this is the question that we pose. Okay, so as a matter of fact, it turns out that it should be possible, and this can be done by a reversal of weak measurement via another weak measurement. Okay, so here is sort of a systematic way. In the box, I describe the evolution in terms of time as far as the state is concerned, and then with arrows, I describe the setup. So, for example, if I start with a state which is alpha 0 plus beta 1, okay, so it's a qubit state. Okay, so now it is undergoing decay, okay, this decoherence. But we are assuming in this case that the detector does not click. So we are talking about those measurements where the detector does not click, which is what we call weak measurement. Okay? So in that case, what happens is that the amplitude of the state 1, that decreases. Okay, 1 minus p square root, 1 minus p happens to be equal to e raised to minus 2 gamma t. So it goes down as the amplitude of the state 1 goes down as e raised to minus gamma t. Okay. So that means that some decoherence is taking place. So the way to recover this state, the original state, is in these couple of steps. In the first step, I apply a pi pulse. That is, 0 turns into a 1 and 1 turns into a 0. Okay. So this is now my procedure to erase the information and restore the original state. Okay. So if I apply a pi pulse, then 0 goes to 1 and 1 goes to 0. And I now, in my measurement process, do another weak measurement. I let the system evolve such that the detector does not click. Okay, if it clicks, game is over. But if it does not click for a certain amount of time, then as a matter of fact, this one in this step acquires also an amplitude which goes like e raised to minus gamma t. Zero already had an amplitude e raised to minus gamma t, so the resulting state will be alpha 1 plus beta 0. And then we can apply a pi pulse, which is a deterministic pulse, to recover back the original state. So a weak measurement coupled with pi pulses, as a matter of fact, can reverse this decoherence process. Okay? Another simple way of looking at it is that supposing instead of a qubit, I have a qubit. I mean, I have a system with three possible states, 0, 1, and 2. Then under weak measurement, as we have talked about, the amplitude for 1 will go down by a factor e raised to minus kappa t, and for 2 it will go like e raised to minus 2 kappa t. So this is the weak measurement. The decoherence has taken place. I get some information, but the price I have to pay is that the state has decohered, and I cannot. The challenge now is to recover, to reverse this process and recover the original state. Okay, so the first step will be, as I mentioned in the previous example, where it was a qubit state, so I could do it from 0 to 1 and 1 to 0. So here I go from 0 goes to 2, and 1 goes to 1, and 2 goes to 0. So then the resulting state is now a superposition again of 2, 1, and 0, but the amplitudes are shifted in different with different photon numbers. And then in this measurement process, we do another weak measurement. So now a state with 2 photons will damp with e raised to minus 2 kappa t. 1 photon will damp with e raised to minus kappa t, and 0 photon cannot damp. Okay. But in this case, we immediately realize that now e raised to minus 2 kappa t happens to be a common factor, and the resulting state is, after doing this reversal of states, 0 going to 2, 1 going to 1, and 2 going to 0, we recover back the original state. Okay. But this is not done deterministically. I mean, that is a very important point. This is done probabilistically. Okay, I mean, this is the situation. This reversal takes place only with certain probability of success. It does not happen in a deterministic way. And the probability comes in because if I have this detector which does not click, so that is a probabilistic event. Okay, so if it clicks, then the state collapses to a particular state, and all the information is gone. So one has to keep this thing in mind, that here we are gaining some information, but the price that we pay is, and we'll see it quantitatively, that the price that we pay quantitatively is conjugate to the information. The more information we get, the the less is the probability of success, and so on. Okay, so here we see this notion of getting some information, that if supposing I start with a state psi, which is a superposition of 3 possible states, 0, 1, and 2. Okay. Then it turns out that in the process of weak measurement, amplitudes Cn acquire another factor e raised to minus gamma, minus n times gamma t. And this amplitude now keeps increasing for lower photon numbers, and decreasing for large photon numbers. Okay, and here I show it in the curve, and we can see that if we start with the same probability for 0, 1, and 2, as the time progresses, the probability of having no photon is increasing, but it will never become equal to 1. Okay. But it is increasing at the expense of C1 and C2. And in this process, we are gaining some information about the state as the time goes on. But the full state is still intact in the sense that the superposition that the state is in contains some information about C0, C1, and C2. As the time goes by, then, of course, all the other amplitudes except for C0 damped to almost zero, but again, never equal to zero. Question is, okay, so the first question that we ask ourselves is, can we quantify information? I mean, here, talking about that it is now large and small, C0 becomes very large and C1 becomes relatively small and so on. How do we quantify information? Okay. Now, this is a whole subject, a very important subject. And here I give you a very, very brief review. I mean, it is a highly mathematical subject, but here I give you some basic notions. If you're not familiar with information theory, that will work for us in order to get the information. How much information do we get in a weak measurement? Okay, so that is the question that we ask. Okay, first of all, we notice that information, if there is information is very closely related to the probability. Okay, if the probability of an event happening is very large, okay, then the information we gain is very, very small. For example, tomorrow the sun will rise. If I tell you tomorrow the sun will rise, okay, now the probability of that event happening is 1, and therefore there is no information there. Okay, absolutely no information there. But if I tell you that tomorrow it will rain, okay, then there is some information because it is a probabilistic event. It is a probabilistic event. Okay, the less likely, for example, if I say, oh, tomorrow the world will come to an end. Okay, now the probability of that happening 0. But that has an infinite amount of information in there, literally. I mean, you will just, we will all scramble and try to take care of what has been left undone. So the less the probability is, the more information we get. And therefore, information for happening a particular event, which I classify as xi in here, but goes something like 1 over p. Okay, p is the probability. But of course, we have to satisfy some properties of the probability, that probabilities of two disjoint events, I mean, they multiply and so on, so on. So it turns out that 1 over p will not be a good measure. Shannon was perhaps one of the earliest persons who tried to put this information on a quantitative basis. So he defined it as log of 1 over p or minus log of p as information. Okay. So this is the information, I mean, this is the definition of information. Now, here we would like to consider conditional information. That supposing if we get an event y, okay, and its probability is yj, what is the information about xi? Okay. I mean, the reason why we are talking about it is because the problem at hand with us is that what is if I find out in my example that there are 5 photons in there, how much information we are getting about the entire state. Okay, so now this is a conditional measurement, that if the measurement of the system y gives us a result yj, then what is the information contained in the variable xi? Okay, so that is given by minus log of the conditional probability xi yj. And then the quantity which is of interest to us is mutual information gained about xi from knowing yj. Okay, and mutual information basically measures how much knowing one of the variable reduces uncertainty about the other. Okay, So, I mean, as on the next slide, we will come back to this example where the states are evolving with time, and we are getting some information about each variable. And what we would like to find out it is getting the information about that variable. How much is the total information that we are getting? Okay, so just to illustrate, and this is given by the information for the event xi happening minus the conditional probability that if yj is there, then what is the result? What is the probability of xi? Okay, or the information about xi, which is related to this conditional probability. So let me illustrate it with two examples. Okay, supposing the two events are completely uncorrelated. Okay, that x does not depend upon y. Okay, what I do in this room does not depend upon whether there is a sun outside and or sun is not outside. If it is completely uncorrelated, okay, so in that case the mutual information that is gained should be equal to 0, because regardless of what is happening outside, I do not gain any information by what is happening outside. Okay, so in that case this mutual information will be equal to 0. But if it is completely correlated, and that is, if it is raining outside, then I am reading a book. And if it is not raining outside, then I'm not reading a book. Supposing this happens all the time, okay, not a good example, but let's say, okay, so in that case, the events are completely highly correlated. This conditional measurement happens to be equal to 1. And in this case, the information gained would be this this mutual information that will be essentially the information that I have about my own system. Okay. Because the outside, whatever happens outside is completely correlated with what I'm doing here. Okay, so these are the two extremes. Now I come to the problem at hand. Okay. Okay, no, before I do that, I mean, I have to add this mutual information for all these elements of xi, yj with the conditional probability that such events will take place, and I have to sum over all possible xi's. Okay, so this is all that we need to know. I mean, I'm sure this is still, one would like to sit down and think about it. I mean, the information theory by itself is not an easy subject. It's highly mathematical, and one really has to sit down. But okay, this gives you at least a flavor of what is happening. So now, if we want to, for example, find out what is the information that we are getting when this weak measurement is taking place. Okay. So this is the question. Okay, we don't want to do in hand-waving way. We want to really quantify this information. So in this case, the initial state is, of course, the superposition of states C and N. The final state at time t happens to be such that there are these decay factors. I'm sorry, I miss a minus sign here. It is Cn times e raised to the minus n gamma t. Okay, so this is the final state. The question is, what is the information that I have gained in this process? Okay, if t goes to infinity, that means or rather, if a strong measurement is made, then of course the information that I gain is maximum. Okay, but what if in this weak measurement where the detector does not click? What happens? Okay, so now we go back to the definition of mutual information and substitute for this conditional probability and the log of this conditional probability divided by pxn, and here we can see that the conditional probability of xn happens to be equal to Cn modulus square. I mean, that is what we all know, that if we have a coherent superposition of state, then the modulus square of the amplitude gives us the probability for that particular state happening, and the conditional probability that if there is no detection event taking place, That is represented here by y naught. Okay. Then the conditional probability now will be for any particular n state would be e raised to minus 2n gamma t Cn modulus square. Okay, because the amplitude in that case for the nth state, for n state, will be Cn e raised to minus n gamma t. So we just square it and normalize it, of course. So this is sort of the measure of information, and then we substitute it in the expression for the mutual information, and we get the idea how much information we are getting if in this coherent superposition of states there is no click. Okay, a weak measurement is made. Okay, so in that case, the total the mutual information looks something like this, and if we plot it, we can now have a quantitative measures. I mean, we have all these numbers, CNs known if we know them, and of course we know what is gamma, and we plug it in here in the expression for the mutual information. We can sort of calculate them and get numbers for each value of time. Okay? And this I plotted on the right hand side. So as time increases, I'm getting more and more information. And again, going back to the example of that room, if I'm sitting outside and nobody comes out for 1 minute, then I'm not completely sure whether there is somebody inside the room or not. Okay, I mean, but my inclination will be that now the probability of somebody inside the room is 90%, not 100%. And then if I wait for 1 hour, then this probability keeps going down. Okay, and after 1 day, this probability is 0.000001. Okay, so I'm getting some information, and here is the quantitative measure. I mean, here I've just sort of summarized that the normalized initial state in the weak measurement part, that happens to go like Cn no click probability goes like summation of these factors, Cn modulus square, and then e raised to minus 2 gamma t raised power n. Okay, so for basically I'm adding the probabilities for all the events that are happening. Okay, in the reversal process that I showed you, where I do another weak measurement. So in that case, what happens is that in that case I basically switch these n's by n minus n. Okay, 0 went to 2. 1 went to 1, and 2 went to 0. Okay, so that is represented here by capital N minus n state, and of course there is this amplitude, and in this case the no click probability basically goes like as it is shown in here. And here what we can see is that as we have this reversal probability, it decreases with time. Okay, so the thing is that to put the things together, that probability goes down. Okay, we get more information, but the probability of success is going down. Okay, it's like let's say. What would be a good example? Let's say an explosion taking place. Okay, so we have an object and something explodes inside, and it is torn into pieces. Okay, so the pieces are still there, but they are not in a composite state. What is the probability that we can bring all those pieces together and form that object all over again? Okay. So that would be sort of the probability of that happening will decrease with the lapse of time, because as the time elapses, all these pieces are really disintegrating more and more and more. Okay, so that is sort of an example of how this reversible I mean, we can get a perfect reversal, but the probability of success decreases in time. So here is sort of this conjugate behavior that I mentioned before, that as time passes in this weak measurement, the probability, the information that we gain, that goes up. This mutual information I, that is going up with time. We are getting more and more information as the time passes, but the probability of putting it back together decreases. Okay, it goes down, and as the time really increases much beyond the decay rate time, it goes almost to zero, but never equal to zero. Okay? So this is that conjugate relationship. The more information we get, the success of this reversible process is less. Okay, so this is the kind of balance we see in nature all the time, that we cannot get everything that we want. I mean, if we get something, somehow we have to lose someplace else. Well, for some people, they get everything. Okay, so yeah. Okay, so I mean, here is sort of a paper that I would like to mention. That here basically we talked about reversing the weak measurement of an arbitrary field. Okay, you can have any state of the field, even incoherent field, not defined by a state vector, but by a density matrix. Even that can be reversed. And the methods that I mention here, there are two methods, multi-atom approach and multi-level approach, and they both are based on what we call stirrup processes. So here we are talking about these field states inside a cavity. So this is a particular system that we are talking about. Of course, it can be generalized to some other systems, but in the cavity kind of system, we proposed a scheme based on stirrup. Now, let me see, how much time do I have? Oh, boy, almost 10 minutes. Okay, so then basically I'll give you just a glimpse of it, not go into too much details, and go to some more interesting part. So okay, so stimulated Raman adiabatic passage basically is a robust way of transferring state from one level to another. Okay, supposing I have a three-level system with two lower states B1 and B2 and one upper state A. Okay, and supposing I prepare it in a coherent superposition of this kind of a state, omega 1 B2 minus omega 2 B1. Okay, supposing it is prepared in this state such that this omega, which sort of in atomic system may represent Rabi frequency, they are time dependent. Okay, the adiabatic theorem of quantum mechanics, which I hope you have all studied, basically tells us that if the system evolves slowly, then this eigenstate of the system will remain the same. Okay, it will not change. So what that means is that if we can change with omega 1, which is time dependent, the state will remain the same. It will be still omega 1t minus omega 2t. Okay. Now from here, what we can see is that if omega 1 is very, very small as compared to omega t, okay, very, very small. So in that case, this atom will be in a state B1 because omega 1 is very small. But if omega 2 becomes very small, then of course the system evolves to B2. Okay, so this is the process that is used in this stirrup process. That okay, so we have this state of the system, and we choose our pulses that are incident upon the atom in this way. That initially, there's the pulse that is sent in this pulse is this omega 2, and omega 1 is not present at that time. So what that means is that in that case, the state will be B1, okay, because omega 1 happens to be 0. But now if omega 1 starts coming in and omega 2 is going away, so after a certain amount of time, there will be omega 1 and omega 2 will be equal to 0. So in that case, the system, the atomic system, will evolve to B2. So now the population has been transferred from B1 to B2 adiabatically, and it is a robust population transfer in the sense that it does not depend upon the details of this pulse. Okay, so that is an advantage. We don't have to worry about how much area of this pulse and so on. So, well, we have used these ideas to really accomplish, to propose, how, for example, we can go from this state C0 0 plus C1 1 plus C2 2 to this weak measured state, and and then of course the reversal process. And here is essentially the basic idea, which I go rather quickly because my time is almost running out and I still have a few more things to talk about. That supposing both atoms in this case happens to be in state C, okay, and this C is coupled to A through this Rabi frequency G, and from A to B by this Rabi frequency omega. Okay, and these atoms, for example, go through a stirrup process to the first laser, and then interacts with the cavity mode, and then another stirrup process. So I just mentioned the first stirrup process because in that case, what happens is that in the stirrup process, now this atom will go from C to B. Okay. So, so in this stirrup process from omega greater than G to omega less than G, okay, those are these two pulses, okay, omega pulse and G pulse. So in that case, CC0 will go to CC0 because there is no photon in there, but CC1 will go to the superposition of BC plus CB. One of the atom will go to the ground state B, which one it is left up to the atom to decide, and we don't know. And CC with two photons, then both of them will end up in state BB. And now here what I show is that, okay, in this arrow, that if I have both atoms in state C, then through the adiabatic passage, it goes to basically this photon number have been transferred to the excitation of the atoms. Okay, so no photon, nothing changes. It is still CC0. If there is one photon, then one of these atoms, either the first one or the second one, they move to the level B. So we have this superposition, and if there are two photons there, then both atoms move to level B. Okay? So this is what we have. And now we apply sort of a pi pulse such that this C goes to B and B goes to C. Okay, so this is a pi pulse between C and B. Okay, with the help of these two waves that I show as omega 1 and omega 2. So in that case, this CC becomes BB and BC becomes CB and so on, and BB becomes CC. And then I apply an adiabatic passage again, okay, and as these atoms are coming out of the cavity. So in this case, in the adiabatic passage state, basically the atoms in BB, they go to CC and so on, and we recover essentially the original state. Okay, there is a misprint of minus sign, so this minus should be plus, and of course now the reversal process will take place, and so on, so on. Okay, so this is sort of a possible scheme with multi-atom swapping, and this is just if we have n atoms, how we will do it. And then here is something with Zeeman level swapping, okay, and something I'll not go through because I have very few minutes left. And I mean, here we have this general Zeeman level swapping, which was studied by Kimball and Zoller and Kimball and their group a long time ago. So this is something which has been demonstrated in the laboratory, and we can use these ideas for our weak measurement reversal. And here I give some possible candidates for the atomic system. Okay, again, no details. Okay, now let me move to this question. Can we reverse weak measurements without another weak measurement? Okay, because the problem with reversing with the weak measurement is that, for example, if the system has decayed by an amount for a time t, then in the reversal process, if another weak measurement is taking place and we need exactly the same time, okay, during which no click takes place. So that is a disadvantage in the sense that we have to wait long time to reverse the weak measurement. So we proposed actually reversal of weak measurement using quantum gates. Okay, so here it is symbolically representing that supposing I have an input state, and here I take the input state to be this qubit state, alpha 0 plus beta 1. Okay, and then the weak measurement takes place. Okay, so in that case, it reduces to 0. It reduces to 0 if a click takes place. Okay, then all the information about alpha and beta goes away. But if there is no click, okay, that is the weak measurement. In that case, the amplitude goes like alpha 0 plus beta, and 1 minus p actually is e raised power minus gamma t. So e raised power minus gamma t1. Okay, so now this is the weak measurement for a certain. Okay, now we want to reverse it, not by making another weak measurement, but by using these gates, one Hadamard gate and control not gate. Okay, and here I've sort of mentioned some details that when I go to the now in the second line, when a C naught, let me see. No, the first thing is the Hadamard gate. Okay, so in the second line, okay, there is this weak measurement state, and Hadamard gate basically turns 0 into 0 plus 1, and or 1 into 0 minus 1. Actually, cosine, I mean, some amplitude, okay, not 0 to 1 and 1 to 0, but rather 0 goes to cosine theta 0 plus sine theta 1, and similarly for 1. Okay, so this is the second line. Then I apply the control not gate. Okay, that is to say that if the qubit whose state I am trying to reverse, if it is in state 0, then nothing happens. If it is in state 1, then the qubit state for the second auxiliary qubit that I'm using in this system, that reverses. 0 goes to 1 and 1 goes to 0. And then and here I choose my what is the Hadamard gate's amplitude, cosine theta and sine theta, to be by this condition that tangent theta 1 should be 1 over 1 minus p, and this is the result. Okay, and it turns out that if after that I take this auxiliary atom and measure it without touching my original qubit, and it turns out to be that auxiliary qubit shows 0, then I have accomplished the task. The state has been completely reversed. But if I get a 1, then it becomes it has become even worse. Okay, so we have to in some sense start all over again. Okay, I mean, why worse? Because instead of beta times square root of 1 minus beta, it has become beta 1 minus beta. So it is like this, that supposing there is somebody gets sick, okay, and very sick and very sick. If that patient dies, the game is over. But supposing this patient gets very, very sick, okay, and we want to make him completely normal person, okay. So now we give him a medicine, and this is the medicine here. So either he will or she will recover fully, 100%, with some probability, or with this medicine, the situation becomes even worse. And then we have to do the process again and so on. So this example sort of illustrates the basic philosophy behind it. Okay, well, my time is up. So in just 1 minute, let me just wrap it up by talking about that similar process could be applied for protecting entanglement. And as a matter of fact, here I've just talked about this null result weak measurement. Okay, that is my source of error, that there is a qubit inside this cavity and the detector does not click, that kind of a measurement. But supposing there is no detector, okay, and there is an amplitude damping taking place. The one of the mirrors is transparent and the damping takes place. That is to say that if there is no photon, nothing happens. But if there is one photon, then it can be either inside or it can decay outside, but I don't know. Okay, so that is the thing. That is like amplitude damping, that you have a cavity with partially transmitting mirrors, and the state inside the cavity sees certain kind of decay. And the question is, can we recover the original state in this kind of measurement? Okay, so we have talked about null measurement and amplitude damping. Okay, so this was a work with which my student, my wonderful collaborator, and another very good friend, Luis Davidovich. So we did many years ago, and it turns out that there is a reversal possible, and we proposed, a system exhibiting such a thing in our paper, which was published in 2010, and it turned out that this scheme of ours was realized almost as it is in this experiment done in Korea. We could publish our theoretical work in Physical Review A, and they could publish their experimental result, the same work, in Nature. So that is the difference between theory and experiments. Since there are students present in the audience, I believe this should be a lesson, that theory is not respected until it is verified by an experiment. Okay, so can we recover entanglement without requiring a weak measurement, etc.? And then we did some more modifications. I mean, we added some preparation stage in these papers, and it turned out that we can, as a matter of fact, recover the state completely in these kind of decoherence processes with almost unit fidelity. Look at this blue curve, okay, almost unit fidelity. So I think, yeah, my time is up, so I should stop. And here is the summary. So what I've talked about is the reversing of the weak measurement, probabilistic method to reverse decoherence, reversing amplitude damping, which is a very different kind of decoherence, and reversing weak measurement and amplitude damping to protect entanglement, not just for a single bit or single state, single particle state, but rather an entangled state. So we have shown ways how one could get around, how one could recover the original state which has gone through decoherence process. Okay, so with that, I think I come to an end to my talk, and I thank again, Orkan, you and the audience for their patience. And again, thank you so much for inviting me, even though I wish I were with you in Istanbul, great Istanbul. Okay, thank you very much.